Okay, today we are going to kind of take a look at that area where rotational and linear motion really cross in together. We're going to look at what it takes to be in equilibrium. Okay, so before we really get started into the idea of equilibrium, we need to kind of look at this thing called center of gravity. Center of gravity is similar to center of mass if the gravity is the same for all elements of a body. It is exactly the same. It is coincident. So, however, we run into problems, especially with things like skyscrapers or things that are noticeably distant from the center of the Earth, is that the gravitational pull is not a consistent value. So here we're going to look at an example of this. So here we have 6 particles. Each have their own mass and they're attached to a rigid structure. That structure has negligible mass. We can ignore it. So we have that the distance between any 2 adjacent particles is 2 meters. So we have 2 meters here, 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 and here. And we want to find the x-coordinate and the y-coordinate of the center of mass, and then again of the center of gravity. So the center of mass. So let's start with part A. So for the x center of mass, we are going to look at the mass times their x position. So each of these particles has a mass m. So for particles 1, 2, and 3, we're going to have mass times 0, because that's where they are in the x position. Now for 4, 5, and 6, they are all 2 meters out in the x position. So we have 2m, 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 and our total number of masses, there are 6 masses. So all total, we are going to get 6m over 6m, which tells us that our x center of mass is 1 meter out. Now our y center of mass, we're going to have for 1 and 6, that's going to be 0. So we're going to have 0m plus 0m. For 2 and 5, we're going to have 2m. So 2 meters up times the mass. For 3 and 4, those are going to be 4 meters up. So 4 times the mass. And again, this is going to be divided by a total of 6 times the mass. So all total, we're going to get 12m over 6m, which tells us that this is at 2 meters. So we have those locations. Now we need to look at the center of gravity. So what are we going to do different with the center of gravity? So here, for the x center of gravity, what we're going to do, here we just did mass times the position. Here we're going to do mass times gravity times the position. So this is going to be the individual masses, gravities, and their individual locations, the sum of that, over the sum of all the individual masses times their gravities. So if I look at this for this particular example, I'm going to have here is mass m, my x position is 0, my g is 8, then I've got for particle 2, my mass is m, my g is 7.8, but my x value is 0. For 3, I'm going to have m 7.6 times 0. For 4, I'm going to have mass m. My g is 7.4. I'm at 2 meters in the x direction. Then for 5, I've got mass of m. My g is 7.6. And I am 2 meters in the x direction. And then I've got a mass of m, 7.8, and I am 2 meters in the x direction. All over the masses times the gravities, so this is going to be m times 8, m times 7.8, m times 7.6, m times 7.4, m times 7.6, m times 7.8. So, a lot to work out. Those first 3 are going to be 0, so we're going to be left with the last ones. And if we do all of this, we are going to get that the x center of mass is going to be about 0.987 meters. So it's not exactly the same. It's similar, it's close, but it's not exactly the same position. If I repeat this calculation with my y center of gravity, I'm going to have, well, 0 times mass times 8, 0 times mass times, what was 6? 7.8. And then we would go up, and these are both 2 up, so I've got 2 times mass times the gravity is 7.8. 5 has 2 times mass times 7.6 from right here. Then 3 is 4 times mass times g. Let's see, 3 is 7.6. 4 mass and g at 4 is going to be 7.4. And I'm going to have it over the entire total again. So we're going to have 8m plus 7.8m plus 7.6m plus 7.4m plus 7.6m plus 7.8m. And if I do all of that work and all of that simplification, I'm going to get that it is just about 3 centimeters shy of where we found it. So if our G is fairly uniform, you're not going to see much of a difference. However, if it is drastically different, you're going to see a huge jump in those changes. So what does it mean for an object to be in equilibrium? We state that an object is in equilibrium if a couple conditions are met. The first of those is that the linear momentum of the center of mass is constant. That means that the acceleration is 0. That basically means that the net force is 0. The only way the linear momentum of the center of mass could be constant is if the velocity is constant. So net force would have to be 0. The second is if the angular momentum about the center of mass is constant. Well, what does that mean? That means that the angular momentum has to be the same, which means there can be no change in it, which means that we're looking at a case where the net torque is 0. Now, there's a slight difference between just the basic equilibrium and what we refer to as static equilibrium. Static equilibrium means that it is completely still, period, end of story. It's not moving in any way. So, if we are looking at just equilibrium, we could look and see which of these would be in equilibrium. So here we have a book resting on a table. Momentum would be 0. Angular momentum would be 0. It is not moving, so that's good. Here we have a hockey puck sliding with a constant velocity across a frictionless floor. So we do have that linear momentum is staying constant. So that could be good. So here we have the rotating blades of a ceiling fan. We really just don't know enough information there. We don't know if it's speeding up. We don't know if it's slowing down. We just know the blades are rotating. And then we have a bicycle that's traveling along a straight path at a constant speed. So the angular momentum should be staying the same because the linear momentum is as well. So for static equilibrium, the external forces have to sum to zero. The external torques have to sum to zero. And here's a different one. The linear momentum has to be zero. Cannot be moving. Okay, so here we have a uniform beam, has length L, has a mass of 1.6 kilograms. It's resting on 2 scales. And then we say, okay, we're going to set a block on it that has a mass of 2.7 kilograms. And its center is L over 4 from the left end. So it's right here, L over 4. We want to know what each scale reads. Well, first things first is to realize that we have a force situation, that the net forces should sum to zero. So that means force on the left plus force on the right minus force due to gravity of the block minus force due to the gravity of the beam should sum to zero. So that means force left plus force right minus big mg minus little mg should give me 0. Well, that seems all fine and dandy, but I could also look at my net torque. Now I have 2 unknowns. I need a second equation. So what I could do is I could say, okay, well, I need to find one of these. So what I'm going to do is I'm going to let this be my pivot point, the left side. So I'm going to let that be my pivot point. So if that being the case, my net torque would be big M G, my distance, which is L over 4. Now that would be making it go clockwise, so that would be a negative torque. I would have the mass, so mass of the beam times G times L over 2. It would also be negative because it would be making a clockwise rotation if this wasn't here. Now this force is going to be making a counterclockwise rotation, so that's going to be positive, and that's going to be force right times the full lever arm L. And this should sum to 0 if we are truly in equilibrium. If we are truly at rest in static equilibrium, that should sum to 0. So what does that mean? Well, that means force right times the lever arm is going to give me big M L over 4 times G plus little m G L over 2. Now there's an L in every term, so those L's are going to ditch. So what I get is that force right is going to equal m G over 4 plus little mg over 2. I'm going to substitute that in over here, so I'm going to get force left plus big mg over 4, little mg over 2. That's going to be minus big mg minus little mg should sum to 0. So if I combine common fractions here, I'm going to have, for the big mg term, that's going to be a positive quarter minus 1, so negative 3/4 big mg. I've got positive 1/2 minus 1, so minus mg over 2. So I get that the force on the left is going to equal 3/4 mg plus mg over 2. Now, if I come up here and I start putting all of my values in, I'm going to get that this is approximately about 28.66 repeating newtons. So just shy of 27 newtons. All right, there's a couple more examples. I'm going to give you guys a chance to work on those. Let me know what questions you have.